Consider the Navier-Stokes equations. This is the equation that describes the flow of fluids. This is a particular case where you have the density term or the fluid density constant. So it's an incompressible flow. Like, for example, you can assume water is incompressible. And in this case, the divergence of this velocity vector here is equal to 0. So in these conditions, this equation describes the flow of an incompressible fluid. And this equation has a particular term here, a second order term, which contains the viscosity of the fluid. So the viscosity of the fluid is an internal friction. The internal friction gives the fluid very special properties. One of these special properties is that close to the walls, what the friction does is that the velocity of the fluid at the walls here is 0. So the Navier-Stokes equations are solved using this condition such that you have a velocity gradient in direction to the wall. Let's say now that you take this viscosity term to 0. So making the viscosity go to 0, the consequence of that is that this whole term here is equal to 0. So you have no viscosity. The rest here, which is left, is called the Euler equations for an incompressible fluid. So this describes the flow of an inviscid or a fluid without viscosity. Now what you have to do is to solve this equation either analytically or numerically to describe the flow field. This term here is an external force like gravity, also called a body force, that exerts a force exerted on the fluid. So if we say that we don't have a body force or an external force, or that this force could be ignored, then you left with an Euler equation in the response to a pressure gradient here. One of the particularities of Euler equation is that it does not say that the velocity is 0 at the boundaries. What it says is that the flow is 0 at the boundaries. So you cannot have flow at the boundaries. There's an interesting property that if you have a constant pressure gradient and if you have velocities that are slow enough so that the inertial terms are small, you're going to have constant velocity, and the velocity is going to be the same as in the interior of the fluid as in the boundary. So here we take a look as a little simulation of the Euler flow on a cross section of a tube. What we did here is to take the viscosity term to 0 of the Navier-Stokes equations and simply solve the Euler equation. So it's a pretty simple condition here. You have a pressure gradient here. So once the simulation is run, you have a pressure gradient. The pressure is higher on the left and smaller on the right, and this drives the flow. And take a look here at the velocity. The velocity of the fluid in the tube, you can see that the velocity is the same everywhere. If we take a look here at the velocity vectors, you will see we can zoom in here, and you see that the velocity vectors are equal everywhere, and at the boundary here of the domain, the velocity is the same as in the fluid. It's a pretty simple simulation of a tube. In the case of a flow of an Euler fluid in a tube, there is no velocity gradient under the conditions of this simulation, just a pressure gradient. And you probably already know that from the Navier-Stokes equation, you can derive the Poiseuille equation or the Hagen-Poiseuille equation, that it's going to show you that there's a parabolic velocity profile along the cross section of the tube.